ago. He was at the University of Illinois. Before that, he's a chaired professor in environmental engineering. We're really happy that Charlie is with us. It's probably not a coincidence that when we moved up to number 2, the university we knocked off was the University of Illinois. And probably isn't a coincidence. We grabbed Charlie and down they went and up we went. So Charlie, come on up and tell us about the cool stuff you're doing with environmental engineering. Thanks, Charlie.
All right. So I know a lot of you don't work in water treatment, and so hopefully I can communicate kind of the excitement of the research that we've been doing and the problem that we're trying to address. And like many of the things that as engineers we work on, we try to come up with innovative, economical, good solutions so that we can solve a major or a significant problem in our own practice. I'm going to talk about nitrate. Wrong button. I'm going to talk about nitrate removal from drinking water treatment plants, and specifically about how to use catalytic systems to treat that. I've worked with a lot of people over the years. This is a list of students and faculty, and down here are some industry collaborators from Catalytic and Johnson Matthey, and they've all had a huge impact. In fact, if you look at who does the work at universities, it's the students. Right? We meet with the students, we help direct them, but they're really the engines of all the innovation and the ideas and putting things together. We're technical managers. We try to help them in that process. As Bob mentioned, just a little bit about myself. I was previously on the faculty at the University of Illinois. In terms of my research and teaching interests, I'm really just kind of the umbrella as pollutant transport to fake porous media. And that could be natural systems or engineered systems. And so I work in hazardous waste remediation, treating water pollutants, which is what I'll talk about today. I also do work in deep geological reservoirs, carbon sequestration, and some oil and gas related work. So today I'm going to talk about catalytic treatment. So when we think about nitrate, if you're in water treatment or wastewater treatment, you might be aware that it's the most common groundwater pollutant in the United States, in the world in fact. And if you look at this map, this shows the probability that a well is going to basically exceed background concentrations of nitrate. And so if you look in the southeast here, Florida, basically 80%, 60 to 80% of those wells that you sample would be above background levels because of high nitrate. And in the Midwest and down in the eastern part of Texas, you're looking at maybe 20 to 40% or so of those wells would exceed those levels. And a high probability or a high number of those wells are also going to exceed drinking water standards. So this is especially problematic in rural areas, oftentimes which lack the resources for treatment. If you're wondering about the source of nitrate, it's primarily agricultural activities. Agriculture, we apply lots of fertilizers. It's anhydrous ammonia, and that ammonia gets converted to nitrate in soils and streams and shallow groundwater. We also have large animal feedlot operations, and so you have a lot of urine that's coming out of those. That hydrolyzes, you get ammonia, and that undergoes nitrification to get nitrate. And you have this discharge from the animal feedlot going into a waste lagoon, and that can infiltrate into groundwater or run off into surface water. Nitrate's toxic, and that's why we care about it. It causes blue baby syndrome, and also it forms N-nitrosamines in the human body, which are carcinogens. And because of that, we regulate it. And if you look at the regulations in the US, it's at 10 milligrams per liter of nitrate and nitrogen. If you look at trends of nitrogen use over time, this shows 1860s, early 1990s, and then 2050. You see the red areas getting redder and getting bigger. And basically it just shows with agricultural intensification over time, we have been using and are expected to use much more nitrogen. And so we're going to keep seeing these problems, and they're going to grow most likely. So how do we treat it? If you look at existing water treatment plants, typically what happens is we have to add a process called ion exchange. Basically, in its absorption-based process, that removes those ions or that nitrate from solution. There are two emerging type of technologies that are mainly in the research stage, although there are a few applications. One is using bacteria or microorganisms to remove that nitrate from water. And the other, which I'll talk about, is using a chemical type treatment method. And in our case, we're using catalyst to treat it. Nitrate's problematic because it has a high solubility, which means a lot of it can dissolve into water. It doesn't evaporate, or it has a low volatility. It's very hard to transform chemically, and that's why these catalysts are needed. And it has a low sorption affinity, or it doesn't bind very strongly to a lot of solids. And so that's why they use ion exchange. If you think about ion exchange, if you're not used to the process, you can think about having these beads that are called resins. And these resins have specific chemistry on them. And that chemistry, it absorbs a negatively charged molecule, or an anion. And so initially they're bound to chloride. And what happens is we take our water, that nitrate-contaminated water, and we push it through maybe a packed bed, like a column filled with these little beads. And when that nitrate moves through, it kicks off the chloride and absorbs to the resin. At some point, the resin becomes saturated. It can't take up any more nitrate. At that time, you have to take that column offline, and then you take a really high concentration salt solution, and you take that salt solution and you push it through, and you kick off that nitrate. And what happens then is you get a really high salt solution that contains nitrate in it. This is a schematic of a commercial process of calgon carbon bins. And in this process, they have different canisters or containers filled with this ion exchange resin. And at any one time, most of them are treating the water, but 2 of them are being regenerated. And so a few of them are always offline being regenerated, and it rotates around. And so basically, you take this water, you move it through, it absorbs the nitrate, and when the resin becomes saturated, you regenerate it with that brine. And typically that brine is disposed of, oftentimes to the sewer. If you live along one of the coastal areas, it might be discharged out into the ocean. Or maybe you might discharge it to a pond where you get evaporation of the liquid, and you're left with kind of a salt solute, or a salt dry solids left that have nitrate and sodium chloride. And that salt, there's a lot of it. We use a lot of it in ion exchange, and it's a waste product. And usually we just use it once. And actually, usually almost always. And because of that, we use about 3 grams of salt for every gallon of water you treat with ion exchange. That's a lot of salt. Okay? It's a ton of salt. So if you think about 1 million gallons per day of water treatment, you're looking at about 2 tons of salt a day. Okay? So it's a lot of salt moving through that water treatment. So what does that mean for the cost? If you look at the economics, about 80% of all the costs of that ion exchange system over the life of the system goes to salt. Right? You're buying a lot of salt. You also have a waste product that has nitrate in it. And nitrate, or nitrogen, is a limiting nutrient in surface water bodies. And so when that runs off, you can get eutrophication of lakes, or you can get, for example, hypoxia in the Gulf of Mexico, where every year you have this large zone that develops in the Gulf that has very low oxygen. When we look at these costs of about 80%, I should also note that that doesn't include brine disposal. And that can range from 60 cents to over $4 per 1,000 gallons of treated drinking water. And when you look at the higher end of those costs are approaching the cost of conventional water treatment itself. So it's a really expensive process. So what can we do to try to reduce these costs? The idea we have is to use a catalytic system where we remove the nitrate from solution using a catalyst to convert it to N2, or just harmless nitrogen gas. There's 2 ways you could do this. You could treat the water directly with just the catalyst, right? But there's a barrier to doing that in the water treatment industry. You know, safety's first, and you want to ease this process in. So another approach we could take that has a much lower barrier for entry is to still treat the waste, or the drinking water, I should say, with the ion exchange system, but take that salt solution and move it through a catalyst system to remove the nitrate so we can then reuse the salt. Okay? So basically, we take the brine, we remove the nitrate from it, and now we can reuse it again to regenerate that ion exchange resin. And so that's the idea, right? We've also been looking at direct water treatment, but in terms of industry acceptance and trying to get this into a more efficient, economical solution, we think this is the right way to go for now. So what's a catalyst? Right? You all use catalysts every day. Most of you drove here, and there's a magical process in your car called a catalytic converter. And you may not have thought much about it, but when the combustion comes out of your engine, it's not fully combusted to carbon dioxide and nitrogen and water. You've got unreactive hydrocarbons, carbon monoxide, and then these nitrous oxide type compounds. That passes over a platinum and other kind of noble metal mixture. And as it goes through, that catalyst converts it or helps it convert to those harmless compounds, water, nitrogen gas, and CO2. All right? The catalyst speeds the reaction, but it's not consumed or altered. And that's why over the life of your car, you don't worry about the catalyst. Right? It works the whole time, hopefully, unless something goes terribly wrong with your engine and you foul it. So, what's a catalyst in water treatment? The basic idea, I'll come over to this figure, is we have these particles, we call them support particles, and maybe it's activated carbon or silica or aluminum. And on those, we put these little islands of these metals, palladium and indium. The nitrate comes in, and hydrogen comes in. The hydrogen dissociates on the palladium, and then it reacts with the oxygen and strips it out of the nitrate. And so what you get is just water, and the end product we desire is N2, that nitrogen gas. What we don't want is the ammonia. So when you look up at the reaction there, we start with the nitrate at the beginning, and we want it to go all the way to that dinitrogen, the N2. And it requires those metals, palladium and indium. When you look at the size of the particles that we're loading it on, they're typically on the order of millimeters. They're small particles. And the idea is that we load this into a packed bed and flow water with hydrogen in it through that packed bed to get the reaction, all right? Or to convert that nitrate to that nitrogen gas. So that's the general idea. It works very much like a catalytic converter. We also have nitrogen species that are being converted to N2. All right. So in the lab, we measure the reactivity of these catalysts in two ways. One way is we take this little batch reactor. It's a little glass thing. And in the bottom is a stir bar. And we put some of our catalysts. And we bubble in hydrogen. And we have a solution with nitrate in it. And we mix it really fast. And when we do that, we measure what we consider the intrinsic activity of the catalyst. So the highest activity that catalyst is going to get. We can't use that approach in real water treatment systems. We need to use a packed bed, where we pack those catalyst particles in a column or some other sort of system, like this big container, and we flow that water and hydrogen through the system, and they react. Okay? The reactivity here is not the same as the reactivity here. There are other things limiting the reaction, and that's what I'm going to talk about. All right? We'd like to get this reactivity here. Okay. So the first thing we wanted to do was just a little economic analysis and see, well, how much money could we save if we did reuse that waste brine? And so we did some modeling of an ion exchange system. And we ran the system until basically it was saturated with that nitrate. And then we regenerated it with that brine. And we either regenerated 2, 5, or 10 bed volumes of the brine. And just for the sake of presentation, we'll just focus on the 2 bed volumes. The results or the trends are all the same. So basically, if we can reuse that brine 10 times, or I should say 5 times, we reduce the salt cost. This is for 1 billion gallons of treated wastewater. We reduce that salt cost from about $433,000 to $102,000. Right? So a $400,000 savings. That's pretty nice. All right? But if we're going to reuse it, we have to treat it with a catalyst. And there's a cost for the catalyst. And the main cost is the palladium. So this is the same plot I had on the previous page. And here I have a new one. And this one shows the cost of palladium. And there's 2 different bars. We'll just focus on the 2 bed volumes again. The 2 bars show this. how much will the palladium cost to treat that brine if we use the activity of the catalyst we get from the batch reactor, or if we use the activity of the catalyst from a flow-through column reactor. All right? The cost is only $55,000 for palladium if we're using the reaction of the catalyst that we get from the batch reactor. That's a big savings compared, or a small amount compared to the savings of roughly $300,000 we get in salt. But when we look at the column reactor, the best activity we get is pretty poor. It costs $1.4 million for that palladium. That's a high cost, and it's prohibitive. So that means in a practical setup for drinking water treatment, we don't have a fast enough reactor or a good enough system to really treat that brine. It's not economical. All right. So we need a fixed bed reactor that we can use in this system that has a higher activity. Another challenge, or I should say another opportunity, is looking at the environmental life cycle impacts. And if you look at this, this shows environmental impacts, and they're in different categories: global warming, acidification, human health, carcinogenicity. And we can just focus on first this one, global warming. This system is just the ion exchange system. And if you look at the total impacts, everything's normalized to that. So they're at 100%. When you look at the impact from the hybrid system, when we have the ion exchange with the catalyst, those impacts are about the same. All right? And that's in a packed bed reactor. But when we go down to these rapidly mixed batch reactors, if we use those reaction rates, the environmental impacts decrease. And they're maybe half of what they are for the ion exchange system alone, for those global warming impacts. But if we look at another system, this one is, say, non-carcinogenicity, but human health impact, boy, if we use that packed bed reactor, the palladium, that's the black part, it has a huge environmental impact. That's no good. But if we get down to the rates in this batch reactor, the environmental impacts are quite a bit smaller than we have for ion exchange alone. Okay, so we have both financial opportunities, and we also have these environmental impact opportunities, and we want to capture those. So let's develop a better fixed bed reactor. So the first thing we did was we evaluated in that batch reactor the best catalyst formulation for destroying the nitrate. And so the y-axis on this plot is basically how fast nitrate's being destroyed, all right? And the x-axis on this plot is basically how much palladium we're loading on an activated carbon support. And so we found that we get the best activity, right, or the best destruction of nitrate, or the fastest, at around 0.58% of that palladium loaded on the activated carbon. The other thing we wanted to do was see how much palladium or how much indium we need. So we vary the palladium to indium ratio. And we get the best destruction of nitrate, or the fastest destruction, when that ratio is roughly around, 5 to 10. It's at a maximum. All right? So we have a catalyst that has high activity for nitrate destruction, and we want to focus on how can we design a better fixed bed reactor. So we dug into the literature to learn a little bit why the reactor is so slow, all right? Or why the published results that people have done give such slow reactivities. And so we know that we need, if you look at the upper right, we need hydrogen to mix into the water and react with nitrate. All right. If we look at how much hydrogen is needed to reduce nitrate, there's 2.5 hydrogen are needed to destroy 1 nitrate. Okay? So you need about 2.5 times more hydrogen than nitrate. If we look at the amount of nitrate that's in the water, there's about 250 of those nitrates that are dissolved in the water. The most hydrogen we can dissolve in the water is 0.8. So we can only dissolve a tiny bit of hydrogen in the water, and there's a lot of nitrate. So you can't dissolve enough hydrogen into the water, right? And that's what makes the reaction go. So what that means is we have to deliver the hydrogen as a separate phase in the gas, and it has to move from the gas, transfer through the liquid to the surface of that catalyst, and then react with the nitrate. And so the main limitation is what we call mass transfer. There's a mass transfer limitation of that hydrogen dissolving across the interface, moving through the water, and then reacting. And that's what's limiting the reactivity in these packed bed reactors. When we have it in a batch system, we stir it really fast. And what happens is it just compresses this liquid layer, right, or that stagnant film around the particle, and then we get fast mass transfer. But in that packed bed, that's not the case. All right. So what we did was we looked in the literature, and we saw that in the petrochemical industry, they built a lot of trickle bed reactors. And those reactors are optimized in terms of the gas and liquid flow rate to make that hydrogen, or any gas, dissolve into the water as fast as possible and react with stuff that's in the water. Or react into a hydrocarbon and react at a catalyst surface as fast as possible. So we followed that literature and we designed a trickle bed reactor. And our goal, basically, we wanted to maximize that gas-water interfacial area and then minimize the water film thicknesses in that reactor. So our reactor looks something like this, where we fed in the hydrogen as a separate phase, we fed in the brine as a separate phase, and then we had CO2 as a buffer to control pH. And then we measured basically what the reactivity was in this reactor. It looks less pretty when you see it in real life. Things are always prettier in a schematic. And in the lab, you build it by your hands, or the grad student does. And basically, there's two stages up above that have the catalysts in them. And then we just had basically a drainage here. And then we have recirculation going with the brine and hydrogen coming in the top. So we packed it using our optimal catalyst, and then we varied the hydrogen flow rate, and we varied the brine flow rate to look at what the optimal, basically, destruction activity is of this catalyst. So the first thing we did was we varied the liquid flow rate and the gas flow rate, and we looked at how much nitrate we could destroy. And so the gas flow rate, this is the effluent nitrate concentration on the left, and that's the symbol. And then the line is the gas flow rate, which is over here, the hydrogen flow rate. And you see from the line that we're stepping or changing that hydrogen gas flow rate. You also see the colors of the symbols matters. That refers to the liquid flow rate going through the column. And every time we change the liquid flow rate, and every time we change the gas flow rate, the concentration of nitrate exiting the system changes because we're getting different amounts of destruction of that nitrate. And you can see at the lowest liquid flow rate of 300 mils per minute, and among the highest gas flow rates, we get the most destruction of nitrate. Okay? So, the first thing we did was we plotted up. If you look at this, this is just basically the activity or how fast nitrate's being destroyed in the reactor. All right? And this is the hydrogen flow rate, and then the colors or the symbols are different liquid flow rates. And what you see for all liquid flow rates, as the gas flow rate goes up, we get faster destruction of the nitrate in that system. Right? You also see at the lowest liquid flow rate, we get the best destruction. So lowest liquid flow rate, highest gas flow rate, we get the most destruction of that nitrate. So that's kind of nice. We tried to interpret what was going on based on the literature. So again, we went back to the petroleum, or the petrochemical industry, I should say. And it turns out that as you vary the flow rate, so the trickle flow rate, or trickle flow, would be where I have really high gas flow rate, but low liquid. And the bubble flow would be the other extreme, where I have high liquid flow rate, but low gas. And as you'd expect, when you have high gas and low liquid flow rates, you get thinner films of water on those particles, and you get faster mass transfer across the surface. And that's why our activity goes up. All right. So we built this reactor. We went through all this trouble. We measured the activity. And we find that we get the best reactivity, or the best destruction of nitrate, at high gas and low liquid flow rates. All right. And interpreting that, we understand that as the gas flow rate increases and the liquid flow rate goes down, this liquid film becomes thinner, and we get faster mass transfer of the hydrogen to the surface, so higher reactivity. All right, that's great. All right, but we want to understand it a little more, all right, and try to predict what would happen in a different system. And so we developed a model. And you don't have to understand any math or remember it. If you don't use it, you never remember it. That's okay. Just look at the words. One equation, basically, it modeled how the nitrate in the water flows through the reactor and reacts with the hydrogen. The next equation describes how the hydrogen flows through in the gas and transfers to the water, right? And the last equation describes how that hydrogen in the liquid, how it reacts with that nitrate. So when you combine these together, you can model that reactivity of the nitrate with the hydrogen as it flows through the reactor. And the parameter we're interested in is this grouping right here, that Ka, because that's the mass transfer coefficient. Okay? So we put all that together. And what we did, the first thing is, we just plotted the mass transfer rate constant, so basically how fast mass transfer is, versus how fast we're destroying nitrate under these different conditions. And there's more or less a correlation where basically, as things are being destroyed faster, our mass transfer rate is going up. Right? We already kind of knew that, but it kind of basically informed us or gave us a better description of that. The more important thing was that we used the model to compare two things. One was how fast we're destroying nitrate in the big reactor versus what the reactivity is, right, of these catalyst particles in a batch reactor. And here's the big discrepancy. If you look at our rates, or how fast we destroy nitrate in these well-mixed little reactors, 100, 200, 300, 400. If you look at how well we're destroying nitrate in this big reactor, 2, 4, 6. Okay? If we pack different catalysts in the reactor that have faster and faster rates, it doesn't matter. Our big reactor is not getting any better. It goes up initially, but levels off around 10 or so. We just aren't destroying nitrate anywhere near fast enough compared to the rates we're getting in the batch reactor. It's still severely mass transfer limited. Right? That's a big problem. This is just a comparison with the literature where we show a lot of literature values that we've measured in batch systems and how for our column reactor, we're at the very low end of those. And that's a log scale. So we're really limited by mass transfer. All right, so mass transfer is a bummer. It really limits this process when we introduce hydrogen as a separate phase. All right, the news isn't all bad. If we look at the activity of our system, they're indicated by these bars in this range. We did it with different catalysts. Well, they're quite a bit better than anything that was in the literature for these packed bed reactors. They're about 3 times better than anything that we found that had been done for nitrate reactivity. But, like I mentioned, it's only about 1/10 to maybe 1/20th of what you find in these batch reactors. So we have a big challenge on our hands. So, what can we do to improve this technology performance? So, about 1.5 years ago, and I've been working on this problem for a long time. I started working on it about 12 years ago. Initially, I developed a lot of different types of new catalysts and improved the rates in batch. And then about 5 years ago, we started working with Calgon and Johnson Matthey to look at how to design a better reactor. And we got to this point about 2 years ago, and I said, all right, what can we do? I said, all right, we can further optimize that triple bed reactor performance. And I don't think that's going to do it. We varied the flow rates of the gas and the liquid over large ranges. I think there's really not much we can squeeze out of that. Maybe a little bit more, but not enough to get us where we need to be. We could structure the catalyst support to improve that gas-water mixing. That's a possibility. When you look at air stripping systems, they have these very, engineered supports that allow thin films of water. But because we need very high activity with the catalyst, I don't think those mass transfer coefficients are still sufficient. So we're still not going to get there. Another one we could do, we thought about, was embed catalysts on hollow fiber membranes, right? And deliver hydrogens just by diffusing across those membranes right to the catalyst. And then we have a very short distance for that delivery. And I think that's reasonable, all right? But it requires some fancy synthesis efforts, and we'd have to really put some thought into that. The last effort I was thinking about was to deliver hydrogen electrochemically. We do electrolysis all the time and create hydrogen and water. Why are we trying to deliver hydrogen as a gas? Why don't we directly deliver hydrogen to the surface through a direct delivery of electrons? Basically, it's like a battery, okay? So these were the 2 ideas that I was toying around with about 2 years ago. And so I started to talk to people. And I'm not an expert in membranes, and I'm not an electrochemist. So I had to find someone who knew this stuff. And so when we have a problem and we need to solve it, we have some skills, but we don't have the whole suite, so we go look for other people. And I came across somebody at a conference who's an electrochemist. And so I started talking to him, and we wrote a proposal on it. And so we said, all right, let's propose this new system. So our newest idea, and a newly funded project that have been working about 6 months on now, is an electrochemical system. The basic idea is here. We still have palladium, and we still have indium, all right? But now, instead of using an activated carbon particle, we're going to use basically a carbon fiber mat. And that carbon fiber mat conducts electricity. And what we can do is we can deliver electrons through that carbon fiber mat. And they combine with basically H plus in solution. There's plenty of that in solution. And it creates this atomic hydrogen on the surface, and then that can directly react with nitrate. And so that's our newest thought. And how we would put that in a reactor basically is like basically kind of like a membrane reactor where we spiral line this fiber and we have flow going out through it. And so basically you create a cathode, that's where you deliver the electrons with the support. And it just so happens that the best metals for splitting water, or I should say for dumping an electron on that H plus, are palladium and platinum, the same metals we use for nitrate reduction. And so that's great. And so we started to work on this, and they're developing these fibers, and they're in the process of synthesizing them in collaboration with an electrochemist who works on conductive support type materials. He's never worked on nitrate reduction, but he does a lot of work on water splitting. And so collaborating with him to try to solve this. One other thing we've been working at is trying to develop different types of palladium crystals that might have a higher activity. Most of the limitations are in mass transfer, but there's still room to be gained in getting higher activity on the catalyst surface. And so we've been combining palladium with non-precious metals. The cost of palladium is about, I don't know, $1,000 an ounce, but you can dope silver into the palladium lattice, and it's only $30 an ounce. It's a lot cheaper. And so that's something else we've been working on. And this has been in collaboration with the chemist at UT. So, summarizing, we developed a new trickle bed reactor. We tested it, and the reaction rates are proportional to gas flow rate and inversely proportional to the liquid flow rate. And we get the best activity in that trickle flow regime. However, the reaction rates are still severely limited by mass transfer. They're quite a bit better than any other fixed bed reactor in the literature, but less than 10% of those in these batch reactors where things are really well mixed. And so we still have a long way to go. So our new idea is this electrochemical reactor. Like I said, I've been working on this for a long time, about 12 or 14 years. And if you ask me about 12 or 14 years ago when we would solve this problem, I'd say about 10 years, right? About 10 years away. So now I think we're still about 8 or 10 years away. But that's why in academics, we come up with really challenging problems for students. And we've made real progress on this. We understand why it's not working. We've quantified that. And really, it's the engineering. Right? It's not the material science. It's the engineering and trying to overcome this problem of mass transfer. So that's what we're working on. And so, if we can use catalysts in these applications, a car, or in a petrochemical refinery, or a hydrogen fuel cell, then why not for drinking water treatment plants? Thanks.
I know you considered it, you must have considered it, but you didn't mention it. Gas is really susceptible and sensitive to pressure. Did you vary the pressures?
We have before. We have done, or worked with a pressurized reactor, and you can dissolve, I think, I can't remember how many bars we got up to. Maybe it was 10 bar. You're still limited in the concentrations of nitrate that we have in the brine at that pressure. You could go higher and dissolve more hydrogen in the solution. The challenge becomes the economics. And so when we were working with Calgon, each kind of alternative design, they went through an economic analysis. And when we get to high pressures and high temperatures, the equipment, instead of using PVC, you can change over to stainless steel. It's a corrosive environment, and the costs just skyrocket. And so that's the limitation. But good question, good thought.
When I have the water with a high nitrate and have to take it out, what is the best process to use right now?
The most economical process is ion exchange. The two that are used, well, ion exchange is the most widely used. If you have nitrates in a salty solution or saline water, then you could also use reverse osmosis. But really, unless you have salts in there, it's ion exchange. It's still quite costly, and you can see, depending on your disposal options, it can be more than the cost of the rest of the plant. And you have a lot of waste product, but by and far, it's the most economical approach still.
Why did you use activated carbon?
Yeah, well, we looked at different supports. The commercial supports, which you need to work with, or at least if you're going to have someone make them in bulk, are alumina, silica, and activated carbon. And we've looked at all three. When you look at treating fresh water, the rates of nitrate destruction that we get using alumina and activated carbon are pretty comparable. But when you look at a really salty solution, the rates that we get on activated carbon are quite a bit higher. And we don't understand why. And the surface charge of the activated carbon must have a lot to do with it. But you're thinking it has mainly carboxylic acid groups on it. It's negatively charged. The silica or the aluminum is also negatively charged, like the nitrate. So I don't understand. But just kind of empirically, that's what we found. Yeah, good question.
So the electrochemical approach, does that introduce a problem with pH control?
Any of the reactions introduce a challenge with the pH. What happens during nitrate reduction is you basically get an increase in pH. You're producing hydroxide ions with that reaction. And I don't think it is any more with the electrochemical. You're still, basically, if you look at the reaction equilibrium, you're producing the same thing. But yeah, and so in our reactor, we buffered it by putting or dissolving basically bicarbonate into the system. You could also add HCl as you're doing it, or buffer with something else like a phosphate. A lot of waters or drinking waters are naturally buffered, and so they might have enough natural buffer capacity. I don't know, but yeah, you always have to pay attention to that. Yes.
You say worried about influent and affluent and nitrate concentrations. What are the ratings that you're working with?
Yeah. So in this case, well, if you look at drinking water, and you kind of look at surveys of where people have looked at drinking water sources, usually you're in the many tens, perhaps low hundreds of milligrams per liter. It's pretty low, right? In our case, we're treating the brine that comes off of an ion exchange resin. And now you're looking at basically 10,000 milligrams per liter or 15,000 milligrams per liter. It's much, much higher than what you would find in the drinking water because you concentrate it when you push it all off that resin with that brine. And so it's a really high concentration. And really, we only need to remove it down to, say, 500 or 1,000 milligrams per liter to reuse that brine for that ion exchange regeneration.
What extent does the city of Austin use the nitrate removal from water here in Austin?
Yeah, I don't believe we have a nitrate problem in our water, so it's not in our drinking. It's not something that we have to treat for. Unless, please correct me if I'm wrong. Ron?
I work for Austin Water Utility. So we do not have a nitrate problem in our source water, Colorado River. Extremely low. So we don't need to treat for this. Very fortunate.
I think if you look at areas where there was a lot of agriculture and cities have been expanding out, you find many more nitrate problems. In the Midwest, along the coast in California, those have been the main drivers. I think the other challenge would be in wastewater where you have nitrate. I think the technology that we're developing, I think it's better suited for drinking water right now. There'd be a lot of challenges with fouling, I think, in wastewater because of all the dissolved organics, and that would be, I think, another issue that had to be addressed.
But for wastewater, I think biological systems are probably the best.
I agree.
So far.
Yep.
Charlie, how much difference do you get in efficiency when you use the electrochemical with hydrogen?
Oh, we're working on it. I don't know yet. Yeah, that's a new project we have, and that's kind of showing you the thought process and now what we're starting with. Yeah. And we've been working on it for about 6 months. Industry's a lot faster than academics. You know, we have a grad student toiling away in the lab every day, and you know, so ask me in about 2 years.
Okay, thank you very much, Charlie.